I want you guys to think back to the pivot lab that we did with pucks of dry ice on an incline. Every one of you was assigned a different trial, and you calculated the acceleration of your dry ice puck down an incline. And then we analyzed all the data as a class. We came to two conclusions. One of them was that actually, it was sort of surprising at the time, the mass of the object didn't matter. Whatever mass, we had different masses of dry ice pucks, and that didn't affect the acceleration. That was maybe surprising at the time, but hopefully by now you're starting to realize that this is a little bit of a theme in physics. We're finding this happens relatively often, where the mass of the object doesn't have the impact on the physics that we think it might. So keep an eye out for that. That kind of thing is going to keep happening. We saw that in our sample problem about friction, where we were not actually given the mass of the object in the problem, and it turned out it ended up on both sides of our equation and canceled out. That's going to keep happening. So keep an eye out for when that's going to happen, and don't be thrown off. Anytime you're given a physics problem and they don't tell you the mass, sometimes that's its own hint that very often in physics the mass doesn't affect the outcome. But the other conclusion that we came to in that pivot lab was that the angle of the incline did matter. So we had this ramp, and as the ramp got more and more steep, the acceleration that we recorded the dry ice puck undergoing got bigger and bigger as that angle got more and more steep. And some people at the time were maybe a little bit surprised because, until they thought about it deeper, because obviously what causes the puck to slide down the incline is gravity. And so people at first were just thinking, well, shouldn't I be getting negative 9.8 meters per second squared since the acceleration is happening due to gravity? But of course, you just have intuitive experience from living your life in the world, but that's not what happens. If I put something on a really, really shallow incline, it's going to go down very slowly. It's not going to accelerate nearly as quickly as if I just drop it into the air. So that's, again, a case where you don't want to get so hung up in the numbers and the equations that you forget to apply your experience with the world and what you know about it. It makes perfect sense that as the incline gets more and more steep, we're going to see a bigger and bigger acceleration, and it's not until the incline is not even an incline anymore, but we're just dropping something 90 degrees to the surface of the Earth, that then we would get negative 9.8 as our acceleration due to gravity. So we have a practice problem here that I'm going to show you how to actually analyze mathematically. But the first thing I want to point out is that it's happening on a 32-degree incline, and therefore we're getting this acceleration due to gravity, the acceleration down the incline at 0.3 meters per second squared. And again, this makes sense because we wouldn't expect negative 9.8 unless we were just dropping the object. So I'm going to draw this situation so we can put a free body diagram onto it. It's got a 32-degree angle down here in the corner. And I'm going to draw the free body diagram just right on top here. I'm not even going to draw the box. It's going to be the dot representing the free body diagram. What forces are happening here? Really simple. As always, we have gravity pointing down, and then we have a normal force that's perpendicular to the incline, to the surface. So drawing this much of it should be pretty easy. We've done this a lot. But now the question is, how can we start to analyze this? The next step in our problem-solving process is to add up all of the forces in one direction and set that equal to ma. The trick here is to realize where the acceleration points. Acceleration is a vector. The acceleration that we have, we're going to have to add up some forces, set it equal to ma, and that a is down the incline. The acceleration that we know about is pointing in exactly this direction, this 32-degree angle. So I couldn't add up all of the forces in like the x direction and set that equal to 15 kilograms times 0.3 meters per second squared. That makes no sense. I've got to add up, if I'm going to set something equal to 15 times 0.3, it has to be the forces that go in exactly this diagonal. So that's where I'm going to put my x-axis. I'm going to look at my problem, and I'm basically going to kind of just tilt my head to the side and shift all of my axes so that my x-axis goes along the incline. And then, conveniently, the y-axis is always 90 degrees, right, from the x-axis. And hey, perfect, that lines right up with the normal force. So that's going to be our y-axis. Now the next thing I need to do is split FG into the y component and the x component. So let me actually move my label here so I have room to do this. I need to figure out FG isn't lined up with these axes. So when I go and I add up all the forces in y, I just get Fn, and I add up all the forces in x, there's nothing, and I've never dealt with FG. So I have to put FG into two pieces that go along the x and the y axis, and so they're going to look like something like this and like that. And I mean, hopefully it's really obvious that this FGY is right on the y-axis, and you've got to kind of look a little bit more closely, but you'll see that FGX is parallel to the x-axis. It's on the x-axis. So I draw it this way to show the triangle, to show that these two purple forces add up to the black one. But really, it's more like I can think of FGX, where is it actually acting? Think about the free body diagram. The forces all act on the point that we draw to represent the object. So really, it's like this. FGX is acting all on this object right along the green line that represents my x-axis. So this is how you're always going to want to set up these problems that are operating on an incline. The incline itself is going to be your x-axis. The normal force is going to line up with your y-axis. And then any other forces that are acting in the problem, you have to figure out how to split them up so that they line up with those x and y axes. And then in the next video, I'll show you exactly how to do the trig and calculate what these values are.